So by the end of this lecture, you will be able to explain reversible and irreversible processes and Carnot cycles. What is an irreversible process and what is a reversible process? Also, you'll be able to understand the entropy of a system and entropy generation in a process, right? And also, you'll be able to calculate the entropy change of solids, liquids, and ideal gases, right? So if you want to expand your knowledge horizon about these topics, you can also always look into the reading list that is suggested here in the blue box. All right. So you know that we always look for things to compare ourselves or processes or stuff, anything, right? So for an example, when it comes to conductors, we consider or we compare our conductor with hypothetical superconductors. As of now, according to my knowledge, we don't have any superconductors available to purchase, but whenever we want a conductor, we can see how much resistance this has compared to a superconductor, right? So it gives us a benchmark to compare with. Or else in an exam, we know that 100% is the maximum mark that we can attain without, if we don't give any bonus, 100% is the maximum mark attainable. So somebody says I got 70%, somebody says I got 80% and everything. So we can have a comparative idea where we stand to the best mark attainable, right? So these comparisons are important for us to gauge the processes or systems performance or personal performance, right? So in thermodynamics, we use reversible processes for such purposes. So let's first go into the definition of a reversible process: a process that can be reversed without leaving any change in either the system or surroundings. So which means both the system and surroundings return to their original states after reversing the process. You remember at the very beginning of this class, we discussed a situation. You have a set of students standing in a line and doing one step and taking it back without making any mark on the process, right? So that is not the exactly reversible process that we are talking in the thermodynamics. But you remember, if we created chaos in the class and we came back to the line, still we left some traces. So it was not considered to be reversible, right? So the importance of a reversible process is that that is the best possible process that we can have to do a given process. So we don't create any irreversibilities during the process. So let's go to the next point. Reversible processes are idealized models, which explains the theoretical limits to which actual processes can be compared, right? And that means, let's say, if we have some irreversibilities, they cannot be taken backwards when we return our process into the original conditions. So with the reversible processes, if we use in a given system, if we use the reversible processes, let's say a turbine, if we had all reversible processes in this system, then it can generate the maximum power. Or else when we are trying to do work in a compressor or something like that, if we had reversible process all the way around, then that device will need the minimum power to work, right? There are two things. So basically it means this is the most effective way of doing a thermodynamic process, right? And if you think of the friction pendulum that you see here, sorry, friction pendulum that you see here, then you can see if there was no friction, then it becomes a frictionless pendulum. So once we tip this off, what can you say about the motion? Would it ever end or not? Please use the chat to communicate. I need a lot of communication today because theory section is very important, and it's kind of hard to digest without communication. Okay, so if we do not do, like, if there's no friction and we just add some moment into the pendulum, would that keep on going forever, or would that stop at some point? Any ideas? Exactly. It will go forever, right? Because the friction is the thing that stops. Like, not, this is not exactly a pendulum what I am showing off, but let's say this is a pendulum, and the air friction is the one that decays the energy or dissipates the energy to the surrounding, so that the piston movement slowly mm, stopping. And in actual reality, if there's a frictionless pendulum, that becomes a perpetual machine. So we discussed about perpetual machines, right? So you give unit work to a given machine, and then that does work for the entire life. So in real world, can we have such a pendulum, frictionless pendulum? Can we have a frictionless pendulum? We cannot, right? But we can get very close to it. We can get very close to it. We can minimize the air friction, or we can create a vacuum and do all these things. We can get very close to it, but we cannot create a perpetual pendulum. And that's why you see that we know, when we compare our processes into the ideal system, then we can get an idea of what's going on, right? And when we look into the irreversible processes, it says all the processes occurring in the nature are irreversible. So basically, what does that mean? It leaves some sort of thermodynamic trace when we try to reverse it. So whatever you are doing, if you heat up a coffee, you cannot send that heat back and convert it to the original form of energy that we used, whatever it's, let it be electricity or some chemical energy from a fire, whatever it is. We cannot just return that energy from the coffee back to the original form without leaving any trace to the world, right? And that is the idea of reversible processes and irreversible processes. Let's look into some examples so that you can get this idea more clear, right? So let's look into some irreversibilities. How can irreversibilities occur, right? One example is friction. So let's say if I have my hand like this, and then I have my other hand, and then I rub it against my hand, right? So these two surfaces, or rub it against like this, these two surfaces have friction, right? Let's say I went up and down. So if when I went up, I created thermal energy or heat due to like this friction. So when we take my hand down, would I be able to give that thermal energy back to its original form, or take that thermal energy back to original form? Can we do that? We cannot do that, right? Because what we are doing is, like, when we go up, due to friction we created some heat, and when we are coming down again, we are creating some more heat. We are not reversing the process. So that the friction, we can understand, friction also create some irreversibilities during processes. That is one possibility, or one possible irreversibility that we see in our day-to-day life activities. Okay, now let's look into the second example: heat transfer through a finite temperature difference. Okay, now let's take our coffee cup example. We have a coffee cup, we buy a coffee from Tim Hortons at UBCO, and then we take that coffee and come out and walk towards the EME in a winter day. So we all discussed, or we all agreed, that the coffee is going to cool down, right? With time, as the surrounding is cold, our coffee is going to lose energy in the form of heat. Now, if we walk back to the Tim Hortons from the EME, using the exact same steps, would we be able to get the heat back into the coffee? Would we be able to do that? We cannot do that, because for us to get the thermal energy from a low temperature space and pump it to the high temperature space, we need a heat pump, right? We agreed that. So if we operate a heat pump to do that, then again the heat pump has some irreversibilities. Therefore, we cannot return this energy to the coffee back without creating any evidence or without creating any trace, right? So therefore, heat transfer through a finite temperature difference can create irreversibilities to our processes. And then fast expansion or compression. When we try to, let's say this is a piston cylinder mechanism, and then we plunger this piston, right? And we take it back. And when we hit the first particle front, then the particles move in a certain manner, right? And then it collide with each other, and then it creates some energy transfers and some heat, some temperature increment, whatnot. And then as it goes this way, it created some energy transfers. And when we are taking it back, would we be able to replicate the same particle motion or reverse the same particle motion? We cannot, right? Excellent. That's the idea. We cannot do that. Therefore, in these cases, we can have irreversibilities. And then again, if we mix two fluids, that is obviously mixing with each other, would we be able to unmix it without leaving any trace? Again, we cannot do it, right? So we cannot do it. Therefore, these are irreversible processes as well. And also chemical reactions. So if we create a new chemical composition, then it's without leaving any trace. Let's say we have some chemical compound like we created by reacting two substances, and maybe if we heat it back, then they'll come into their original forms, but still we need to provide heat. So that basically means we have to create some irreversibilities in order for us to take it back. So then by definition, it's not a reversible process, right? So are we all getting a sense what we discuss as this irreversibility? Do we have an understanding? Perfect. And can you also see that if we do not have these irreversibilities, then the processes would be much efficient. Like if we can reverse the heat flow back into the coffee without any other means, without needing any other means, that will be the most efficient way to do it. But practically it's not possible. That's why we need a heat pump, right? If we can, like if our piston, like let's say in a piston cylinder mechanism, when our piston goes this way, it creates friction. If we were able to reverse the friction when we are coming back, then the energy losses in our engines or our other machines due to friction will be avoided. So can we all agree that if we can have the processes in a reversible manner, then that would be the most efficient way to do it? Can we most effective or way to do it? Can we agree on that? Anybody? Perfect. So now let's look into Carnot heat engine, right? So we discussed about heat engines before in the last lecture. You remember in the boiler, we heat the water and create steam, and then the heated steam goes through a turbine in this case, and then after expanding through the turbine, then it goes to the condenser and dissipates some heat into the sink, and then goes through the pump, and the cycle continues. So this was the heat engine, right? The Carnot heat engine is the most efficient engine that can be defined, reaching the theoretical limits. So we agreed if we can operate or if we can do the processes in a reversible manner, that will be the most efficient way of doing that thing. Then, without contradicting with that statement, we can agree if all the processes that we see in a heat engine becomes reversible, then that engine should be efficient than any other engine operating under the same conditions. Can we agree with that? Are we making sense here? Perfect. Now you see why I told you by the end of this course, you will have means to argue if a friend said, okay, my efficiency or my vehicle's efficiency, not my efficiency, my vehicle's efficiency is 100%, then we would say, okay, no, you cannot have a gasoline engine with 100% efficiency. And then he or she might say it is 90%, and we would still say, okay, it's practically impossible to reach that number, right? So how do we say that? It's based on the Carnot efficiency. So if the Carnot engine is the best engine that is possible according to the theoretical limits, then you cannot have more than that. You cannot have a better efficiency more than exceeding this thing, right? It's like when we evaluate an exam from 100%, no bonuses, no nothing, just evaluating the exam. Somebody says, I got a 200%, but the theoretical limit was 100% score. And somebody claims it's more, I have a mark exceeding 100. That is impossible. Other than the markers did a mistake or something, other than that, there's no way that that person can score a 200, right? So similarly, in a practical heat engine, it cannot exceed the efficiency of a Carnot heat engine. So in a Carnot heat engine, so we have 4 processes. The first one is indicated from A to B, reversible isothermal heat addition, right? That is where we create the steam in the previous example, right? And then reversible adiabatic expansion. So you see the word adiabatic here. So there, like, no heat transfer, and it is reversible again. And then reversible isothermal heat removal, right? So you remember we said the heat removal is itself is an irreversibility, but still, if we can have that process in a reversible manner, that is the best possible way of the theoretical limit, right? Let's say if there's a tough exam that nobody can score 100 within that given time frame, then we cannot say that we can achieve 100, but still the theoretical limit, the theoretical best possibility is achieving 100, like that, right? And then the 4th process, reversible adiabatic compression, in which the temperature rises from TL to TH. Okay, so if you look into the points given at the very end, the Carnot cycle is reversible, right? This is very important. So Carnot heat engine have the maximum efficiency. You remember, for refrigerators and heat pumps, we don't use the term efficiency. Instead, we introduced ourselves to the concept of coefficient of performance, right? So if you think along the same line as we discussed about the Carnot heat engine, if we can define a Carnot refrigerator, if we can develop a Carnot refrigerator or a Carnot heat pump with involving all the reversible processes, then it should give us the most benefits, right? In the sense of energy efficiency. So that's why we are getting the highest COP for refrigerators if it operates under reversible conditions, which we call a Carnot refrigerator or a Carnot heat pump, depending on the application. Do we make sense here? Can we all establish that Carnot heat engine is the maximum, has the maximum efficiency that we can achieve in a thermodynamic heat engine, and a Carnot refrigerator has the best COP for a refrigerator, and Carnot heat pump has the maximum COP for a heat pump. Are we all in agreement? Perfect. So now we have a new 100% score, right? So we know that this is the theoretical limit. This is the best we can achieve, and then we can compare our devices into the best possible number and where do we stand, and we can evaluate how can we improve, right? So the same idea. It's very important that we establish these theoretical limits. Otherwise, we'll be disappointed. Let's say we get a 40% efficiency in a gasoline engine, then still we'll be beating ourselves saying, okay, we could have achieved 100%, but practically we cannot achieve 100%. Now we don't have to worry. The maximum efficiency, let's say, under given conditions, the maximum efficiency is the Carnot efficiency, which could be, let's say, 50%, and we are at 40%. So now we feel safe, and we know, okay, we are very close to the ideal conditions, right? Now, you remember, this is how we indicate a heat engine in general, right? We established this one in the previous class. So we receive some heat from a high temperature source, and which is indicated by QH, and then again we emit some heat into a low temperature reservoir while producing work, right? I believe all of you remember this from the last class. And with this one, we established that the thermal efficiency for any heat engine is given by this expression up there, right? So we are familiar up to this point. And now for reversible processes only, for reversible process, we can say that QH over QL is equal to TH over TL, which means the heat received from the ratio between the heat received from the heat source and the heat ejected to the heat sink is equal to the ratio of temperatures of the heat source and heat sink. And this temperature, very important, is given in Kelvin, right? So this is a very common mistake that many students do in the exams and evaluations. So if you are using a ratio of temperatures, and if you are not sure whether to use Celsius or Kelvin, if you are not sure, always go for Kelvin, right? So anyways, in this case, the ratio should be in Kelvin. If you apply this ratio in Celsius, it's going to be a different answer and it's going to be wrong, right? So now for a reversible process, we agreed that this relationship stands. If this relationship is true, for a reversible engine, we can say that the thermal efficiency of a reversible engine is going to be given by this expression. Are we all clear how we came up to that point? Carnot heat engine is a reversible engine. Therefore, we can substitute for QL over QH by TL over TH. Then we came across this engine or this efficiency. Are we clear? Perfect. Did everybody get it? So Scott got it clearly. That's very good. How about the others? Are we all in the same page? The entire class? Perfect. Perfect. Thank you. And now with this one, you see that when your friend come to your house and say that, okay, I got 100% efficiency. Now you ask them, what is the temperature of your heat source. So in a gasoline engine, at the detonation point, the temperature, right? And the heat sink would be the surrounding. So TL is going to be surrounding temperature, and TH is going to be the burning fuel air mixture temperature. If that person can give you that information, then you say, aha, you cannot have 100% efficiency, and this is the theoretical maximum that you can have. And you have violated the second law of thermodynamics if you have gone beyond that efficiency, right? Now let's look into some evaluation or some analysis techniques. If, let's assume this is our friend's engine efficiency, and he or she says an efficiency value which is less than the reversible engine's thermal efficiency under these given conditions, which is Carnot efficiency under these given conditions. If our friend's efficiency is less than our reversible efficiency, then we can say that it is an irreversible heat engine. Can we have this engine in our practical world? Can we have this? Anyone? Can we have an engine which has an efficiency less than Carnot heat engine? We can, right? That is the whole argument. So if it is a reversible engine, that is a theoretical maximum, but in practice irreversibilities occur. Therefore our efficiencies are always less than the Carnot efficiencies. That is a practical engine, right? So we can have that number. And if our friend says, okay, my efficiency is equal to the reversible heat engine, then you would say, like, I think you are thinking too much about your engine, but that you have reached the theoretical maximum, because reversible processes are very difficult to achieve or almost impossible to achieve in practical realities. Therefore we'll say, but we'll give an extension and say, okay, I can still agree to believe you. I'm not fully convinced that you made a Carnot engine, but still I will agree. But then the friend does not stop there, and they want more to impress you, right? So they say, okay, my engine has a better efficiency than the Carnot engine or reversible engine. So do we agree with that statement? Do we agree? My engine has a better efficiency or higher efficiency than the Carnot engine or reversible engine. Do we agree with that? We don't agree with that. That is impossible, right? So unless they invent a new thermodynamic process to do these things that we or nobody else in the world knew up until this point, they cannot do that. I'm not saying that we cannot do that. Maybe with innovation and inventions, people may have come up with a different process, but with the current process, current thermodynamic process that we are using in heat engines, this is the maximum that we can go, or this is the best we can achieve, right? Okay, so similar to heat engines, we discussed about heat pumps in the last lecture, right? What does it do? It absorbs heat from a heat sink, and with some work input, it ejects it into the high temperature source, right? So for a refrigerator, the purpose is removing heat from the heat sink. Like for refrigerator, the important part is removing heat from the heat sink. For a heat pump, the useful thing is to receive heat in a high temperature place like our house, right? So both these things are requirements. So depending on the desired output, in the last lecture, we defined our COP values for the refrigerator and heat pumps. So are we clear up to this point? Do you remember these expressions from the last lecture? Anybody? COP, coefficient of performance. Perfect. So we defined coefficient of performance rather than using the term efficiency, because COPs can go beyond 1, right? So it can have a value greater than 100%. Therefore, to avoid any confusions, we are not using the term efficiency here. Rather, we are using the coefficient of performance. Now, from the previous, not the previous slide, the slide before, we agreed that for reversible processes, we can write QH over QL equals TH over TL, right? Therefore, we can say that for a reversible refrigerator or a Carnot refrigerator, we can write the coefficient of performance of a Carnot refrigerator using this expression that you see here. Similarly, for a Carnot heat pump, we can get the theoretical maximum or maximum COP using this expression. Are we all clear on that one? I'm sorry, I'm asking the same question again and again, whether we are clear or not, because I just want to make sure that we are building on this story, right? Because if we miss one block of the puzzle, then you will be struggling on that one in the coming slides. That way, you will not get the lecture. So I don't want that to happen. Okay. Perfect. So now you are getting slowly there. You remember, okay, Deza, go ahead. Are all isothermal processes are reversible? No, it's not. So being isothermal is not enough. So you have to make sure that during the process there are no irreversibilities that we, similar to the examples that we discussed here there in the slide. So even being isothermal, the process can have some irreversibilities. So being isothermal doesn't mean that it's necessarily a reversible process. Did I answer your question, Deza? Perfect. Now, we define the thermal efficiency of a Carnot engine using the expression that you see here, right? And then you see if the heat source that we are dealing with have a higher temperature, a greater temperature, what can you say about the efficiency value? When TH goes higher and higher, what happens to the efficiency value? Should it go higher or lower? It gets higher and higher, right? Because TL divided by TH gets smaller and smaller as TH goes higher. Therefore, the Carnot efficiency is increasing continuously. So if you look at this figure here, the surrounding temperature is given as 303 Kelvin, roughly 30 Celsius. And now for this table gives you the thermal efficiencies if our heat sink has different temperatures, 925 Kelvin, 800 Kelvin, 700, and different numbers of temperature, right? So you can see that where the temperature drops down, the thermal efficiency is also dropping down, the high temperature source temperature, right? If it is dropping down, then the efficiency is also dropping down. And that is why we discussed the quality of energy. The quality of energy. When we have a high temperature, then we can do more work, right? It's easy to convert into other forms. You remember in a previous lecture, we discussed work has a higher quality compared to heat because work can be easily converted into some other forms, including work can be converted into some other forms, including heat, very easily. We just put a stirrer in a coffee cup and we rotate it so fast, and then still that will create thermal energy, right? But if we just put the thermal energy back into the coffee cup, would it be able to stir the stirrer? No, because it's relatively harder to convert heat to work compared to converting work to heat. Therefore, we say work is high quality energy compared to heat. Similarly, a high temperature, a higher temperature energy, high temperature thermal energy is easier to convert into some other forms compared to low temperature energy. You remember when we were discussing this quality thing earlier, so you remember we had a mounted tank from the floor level, and we said that this is filled with water, and again let's say this is filled with water as well, and then we pinch a hole here. Sorry. Then we pinch a hole here, and then the water comes this way, right? Water does not tend to go upwards because it's harder for us to convert this low quality energy into high quality energy, right? Are we making sense here? Can we all agree that thermal energy at a higher temperature has a higher quality or ability to do work, ability to do more work, or easily do work, right? We can agree with that. Okay. And I appreciate all of you who are involved in the chat because that helps the class move on. And at the same time, those who are not involved in the chat, like there are no good or bad questions. If you understand and decide to stay quiet, that's your choice. But if you do not understand, please put a chat so that we all know that we can discuss that point. Sometimes one question can direct the discussion into a new dimension and get a better understanding, right? So please be involved in the chat as much as possible. Okay. Okay, Reza. Yeah, go ahead. But won't lower TL be better? But in a refrigerator, like a higher temperature in the source, higher temperature in a source is the one that drives the process, right? When we have a higher temperature, then we can drive that heat flow. You know what I mean? The temperature difference matters, and at the same time, higher temperature heat source have the ability to make that temperature or make that heat flow from one end to the other. In this case, in a refrigerator or a heat pump, we have, let's say, in a refrigerator, we have the surrounding temperature fixed, right? So now we need to drive that into drive that heat flow. To drive that heat flow, a higher TH is better. Can we agree on that? Yeah, the difference of temperature is very important as well. Yes, exactly. So higher, like what we agreed here is the higher temperature heat sources can do more work. And when it comes to practical applications for heat transfer, definitely the delta T matters too. TH is always bigger than TL. Yes. Are we all clear? Desert, did I answer your question as well? Perfect. Now, I want all of you to try this example real quick, based on the theory that we learned today. Take 2-3 minutes and try this example. So let's go through the solution process together. So now there's a generic form to our heat engine. So this is our heat engine, let's assume, and then it absorbs heat QH from a TH reservoir and ejects some amount of heat into a heat sink which is at TL temperature, and TH and TL is given. TH equals 300 Celsius, which is 300 plus 273.15 Kelvin, and TL is 45 Celsius, which is 45 plus 273.15 Kelvin. So now we have TH and TL. We know that the thermal efficiency of a Carnot engine or reversible engine, we can say that 1 minus TL over TH, right? Now we can substitute to TL and TH and we can get the answer. And it's very important, again, these TL and TH should be in Kelvin, right? So if you substitute in Celsius, you will get wrong answers and you will not get the marks for the final answer. Very important. A simple point, but very important. And once you get, if you substitute in Celsius, the numbers are very wrong and your conclusions will be wrong as well, right? Therefore, please be conscious and all the time in our second law evaluations for these equations, use Kelvin. Ideal gas law, use Kelvin. Don't use Celsius at all in these conditions. If you are not sure of which unit to substitute in an equation, substitute Kelvin if you are not sure. That will not do any harm. Okay, so now we get our thermal efficiency to be 0.445 or 44.5%, right? Now if one of our friends say that under these conditions they achieved 0.6 efficiency, can that happen? 0.6 efficiency, can that happen? Anybody? Can we have a 0.6 efficiency or 60% efficiency under these conditions, these temperature conditions? Is it a possibility or not? It is impossible because these numbers say that this is higher than the reversible engine efficiency, so we cannot achieve this. Now you see, why did we agree at the very beginning of the lecture series that we'll be having means to defend ourselves and argue, okay, you cannot achieve 100%, right? If we know the temperature conditions that her or his engine is operating at that point, then we can find the theoretical maximum and say, okay, hey, look, this is the maximum you can achieve and you cannot go beyond this, right? Okay, so now for This heat engine, let's say our QH value, QH was given to be 10 kilowatts. And what will be the maximum work output that we can get from this engine? What will be the maximum work output that we can get from an engine under these temperature conditions? Any idea? Excellent. 4.45, right? So eta reversible was equal W max over QH. For the given heat input, the reversible engine produces the maximum work output, right? So in that case, we can simply find maximum work output from a heat engine under the given conditions by multiplying reversible efficiency into QH, which becomes 4.45 kilowatt. Are we clear? Anybody having issues understand that portion? The last one? Perfect. Okay, now try this one. Excellent, Menna. So the answer is 7.07, right? Calculate the coefficient of performance of Carnot cycle heat pump operating between reservoirs. So for a Carnot heat pump, we can write the COP using the expression. And once we substitute for TH and TL, then we can find the final answer to be 7.07. It's very important that we convert all the temperatures into Kelvin. Again, I reiterate it's very important that we convert all the temperatures into the Kelvin scale. So in this heat pump, TH and TL is the low temperature reservoir. We have a heat pump and we have QH and we have QL and we have a work input. What is the minimum work input to this heat pump? In the previous one, we calculated the maximum heat output, maximum work output, and what is the minimum work input to this heat pump? If our QH value again is 10 kilowatt, what is the minimum work input? So for a refrigerator, we define COP is the desired output by work input. Desired output is QH divided by work input W in, right? And W in minimum is QH divided by COP maximum. In other words, the reversible refrigerator or coefficient performance of a reversible heat pump, right? 10 divided by 7.07. Okay, assuming everybody is clear, we can move into the, yeah. So COP was defined as the desired output over the work input, right? So desired output was QH and work input was work input as the name implies. So we substituted and we determined the minimum work input was 10 divided by 7.07. Okay. Now we come across a new section of theory. So I want all of you to take 5 minutes break and then we'll continue this discussion afterwards. So up until this point, we discussed how we can evaluate or calculate the Carnot efficiencies and Carnot efficiency and Carnot COPs for our devices, and therefore we can come into conclusions about whether this given device is practically feasible or it's not feasible or it's just achieved the theoretical maximum, the reversible conditions. So are we all clear on that regard? How to do that? Perfect. Now, let's continue the lecture now. So in a reversible heat engine, you know that these heat engines are cyclic devices, right? So throughout the cycle, we have QH, which is a heat input, and we have heat rejected or heat ejected to the low temperature sink. And these are the two main heat components that we have, right? So if we want to take the cyclic integral of delta Q over T for this given cycle, then that means delta, not delta Q, like QH over equals QH over TH minus QL over TL, right? So for reversible processes, we agreed that this relationship stands. QH over QL equals TH over TL. So if we reconfigure this expression, we can see that QH over TH minus QL over TL is equal to 0 for reversible processes. This is for reversible processes. Reversible. So are we all clear how we arrived at the 0 here? If we want to do the cyclic integral, or in other words, if you want to evaluate the heat over temperature throughout the cycle that we are dealing with, then we can say that delta Q over T throughout the cycle. So we just have two heat components, QH and QL. So QH divided by TH, the temperature of the reservoir it's dealing with, and QL divided by TL. TL is the temperature of the reservoir it's dealing with. And if we do that, QH is positive because it's a heat input to the system, and QL is going to be negative. That's why we added a negative sign there, because it's leaving the system. And we get QH over TH minus QL over TL, but we agreed that QH, or the ratio between the two heat components, is equal to the temperature ratio. So from that expression, we can see that QH over TH minus QL over TL becomes 0. So now you can see that for a reversible process, the cyclic integral becomes 0, right? So for an irreversible process, this relationship does not exist. This relationship does not exist. And at the same time, if that is the case, we cannot say for an irreversible process, we cannot say that this becomes 0, right? So there's an equality defined as Clausius inequality. In Clausius inequality, what it says is for reversible processes, delta Q over T, the cyclic integral of delta Q over T is equal to 0. And for irreversible processes, the cyclic integral of delta Q over T is less than 0. Right? So this is a very important expression that we're going to use in the coming slides. Are we beyond that one? The Clausius inequality. Perfect. Now, with this inequality in mind, let's look into the coming slide. Right? The new property, entropy. We learned about many properties, including internal energy, enthalpy, specific volume, and we learned about all these properties. Now we are introducing ourselves into this new property called entropy, right? And entropy is an extensive property of a substance. What does that mean? If we have a chunk of substance with S amount of entropy, then we divide it into 2, then we have half of the entropy in one block and half of the entropy in the other block. So which means an extensive property is a property that changes with the mass of the substance, right? And similar to other enthalpy, internal energy properties, specific entropy is an intensive property. Specific entropy is an intensive property. The entropy per unit mass is not going to change even if we divide our substance into 2, right? Are we clear up to this point? So we did not discuss how to define entropy and whatnot yet, but are we clear up to this point? It's an extensive property, and if we take the specific form, then it is an intensive property, right? So for entropy change during a given process, we can call it ds or delta S. Entropy change during a given process, entropy change between two states, let's say state 1 and 2, as we see here, right, can be found by delta Q over T across a reversible path. This is how we define the entropy. So don't panic or anything, just bear with me for now. Let's say from state 1 to 2, we have a reversible path as seen by the solid line, and the dashed line shows an irreversible path. The definition says, the definition you see here, entropy is a state property. It does not change with the path we took, right? Entropy does not change with the path we take. Can you remember some similar properties? Internal energy, does it change? Like internal energy difference between two states, does it change depending on the path we take? Internal energy, does it depend on the difference of internal energy between state 1 and 2? Does it depend on the path we take? It does not. It is a state property, right? Similarly, entropy is a state property as well. So no matter however you go from 1 to 2, but the entropy difference is going to be the same. But if we want to calculate this entropy difference, then we have to integrate delta Q over T along a reversible path. To quantify the entropy change, we have to do the integration along a reversible path or reversible process line, which we have done here. Are we clear? Let's name this process A and this process B, right? And this as expression 1. Can we use expression 1 to calculate the entropy difference or entropy change occurred during process A? Can you use expression 1 to find the entropy change during process A? Okay. Can we use expression 1 to find the entropy change happened during process B? Christopher says no. Any other answers? It is a yes, because we said the entropy change between two states does not depend on the path. It does not depend on the path we take. It is a state property. So S2 and S1 depend on the conditions at state 2 and 1 only. Does not depend on the path. And we agreed to calculate or to quantify the entropy change between two states. We have to do the integration alongside a reversible process, right? So either ways, like I mean, whether process A or B, we can use the expression 1 to calculate the entropy change between state 1 and 2, right? Okay. So the area in TS graph under the reversible process curve is heat transfer Q. Yes, the area in this TS diagram gives heat. Not even in reversible process, the area in a TS diagram always gives the heat transfer during that process. Did I answer you, Ella? It can be negative. Depending on the process direction, it can be negative. And entropy change. Okay, that brings up an interesting question. Can entropy change be negative? Can entropy change be negative? It can be, right? Because if our state 2 and when we compare state 2 and 1, if our entropy difference, like if our S2 value is less than S1, then definitely we can have a negative value. It totally depends on if we just reverse the process that we see here, you can see. So it can have a negative value. So it's very similar in that regard to internal energy enthalpy, because they can have negative values and they are state properties, right? So are we all clear? Are we all clear about this slide, the contents of this slide? Perfect. Now we are going to introduce another parameter, entropy generation. Like, so we introduced ourselves into entropy before, that's a property. And we are now introducing ourselves into a new parameter called entropy generation, right? So this is easy to mix up. Entropy and entropy generation are two different things. So we'll see how this goes. Okay. So if you look at the cycle that is created by process A and B, like if you go this way, so this is a cycle, right? This is a cycle. Process A and B create a cycle. So if you integrate, or if you consider the cyclic integral across the cycle completed by process A and B, that is a reversible cycle, right? Because both processes involved in this one are reversible. Are we all in agreement about that? The process is reversible if we just use process A and B to complete the cycle, because there are no irreversibilities, right? So now, if we want to get the cyclic integral, so we have to do the integration from 1 to 2 and 2 to 1. 1 to 2 across process A and 2 to 1 across process B, right? And from Clausius inequality, we knew that for a reversible process, the cyclic integral is going to be 0. So that is what we say in this line. Are we clear? Anybody who's not clear? Or are we clear about this one? The first line. Perfect. Now, similar to the previous step, let's think of a new cycle involving process C and B, right? Involving process C and B. So now, process C is irreversible. So what can we say about the cycle created by process C and B? Is it reversible or irreversible? It is irreversible, excellent. Because even if we have one single irreversibility, that is, the process is irreversible, right? So if we do one mistake that we cannot reverse, so that becomes an irreversibility. So it's going to stay there. So now, then, if we get the cyclic integral of this one from the Clausius inequality, we can say that this is less than 0. The Clausius inequality said the cyclic integral of delta Q over T is less than or equal to 0. This is Clausius inequality. So in this inequality, the equality stands for the reversible processes, inequality stands for irreversible process. Therefore, we can say that as the second cycle we considered is irreversible, we can say that it is less than 0. Can we do that? Are we all in agreement? Are we all clear about that one? Perfect. Now, if you look into this one and this one, it's the same thing, right? Process B is common for both cycles. Therefore, the integral of delta Q over T across this process line should be the same value, right? So, looking at these two lines, we can say that delta Q, the integral of delta Q over T along process A is greater than the integral of delta Q over T along process C. So it's like this. Let's say we have 3 people. So myself, let's say not 3 people, myself, my cat, and my sister, right? I measure my weight with my cat and I record 80 kilograms, 90 kilograms, let's say. I record 90 kilograms. And my sister weighs herself with the cat and it becomes 65 kilograms. Cat was there in both cases. What can you say about the weight of me versus my sister? Is my sister heavier than me or lighter than me? Is my weight higher than my sister? Any idea? Yes, right? Because that is simple math. So myself, me plus cat equals 90. Sister plus cat equals 70. So cat is a common denominator. It doesn't really matter. By looking at this, we can say that 90 is higher than 70. So I am heavier than my sister, right? Similarly, it's the same thing that this expression say. The blue color is the cat, right? It's the common thing. And I say A plus the blue color equals 0 in the first expression, and C plus the blue color is less than 0, right? Then that means we can say that A is greater than the integral A is greater than integral C, as seen in this box. Are we all clear? Perfect. Now, from this step, if we think of the integral along process line A, process A is a reversible process, right? Reversible process. So that means if we wanted to find the entropy change from 1 to 2, DSA, right? Total entropy change during process A can be written by delta Q over T. That is the definition, right? If we have two given points, then we want to find the entropy change between these 2 points, 1 and 2. We integrate delta Q over T alongside a reversible process, which we can agree to be process A. We can use process A to do that, right? So does the entropy change from state 1 to 2 vary if we use depending on the path? Does it change depending on the path? It does not, because entropy change is a state property. So we can agree that entropy change happened during process A is equal to entropy change happened during process C, right? That's what we see here. Can we do that? Can we do that? Are we clear about this last line? This is what we discussed in the previous slide. Entropy change is a state property. Therefore, irrespective of the path it takes, we can calculate the entropy change, total entropy change during a process by integrating delta Q over T along a reversible process. Do I make sense here? Anybody who's understanding or not understanding, you are welcome to mention that in the chat. This last step. Okay. Good so far. Why don't compare B? Because B is like the cat, right? So if our goal was to compare, delta Q over T, integral of delta Q over T along process A versus process C. So we just dropped B because cat was the common thing. So we were interested in my weight and my sister's weight, comparing these two. So cat was just there, so we just omitted the common factor, right? So now if we substitute this DSC value here, we come across this expression. Are we clear about this last step? Are we clear about the last step? This one? Perfect. Now, when we complete the integration, then it says ds is greater than or equal to dq delta q over t. So this equality stands. This equality stands when the process is reversible, right? Right? This equality stands when the process is reversible, and it is always greater than delta q over t when the process is irreversible. So the total entropy change can be written as delta q over t plus a constant, which is always greater than or equal to 0, as seen here. Does this make sense? So now we came up to this point. Entropy change during a process is equal to delta q over t during the same process, right? Don't mistake this. During the same process, which means if you want to calculate delta q over t that we see here, we have to go along the process line and do that, right? And then if we want to, like, let's say ds is greater than or equal to something, then we say that we can add a positive constant to the right hand side and say that ds equals always is equal to delta q over t plus a positive constant. That positive constant sometimes could be 0, and that is when the equality happens in this expression. And sometimes this constant can be higher. That is when the inequality happens in the very same expression that we see here. And that positive constant, we call it Sgen, or entropy generation, and it is greater than or equal to 0. Okay, so now it's time for questions and clarifications. If you understood it perfectly fine, then let me know that. If you have questions, please feel free to ask. Okay, so Alan, are you clear up to this point, this expression? Perfect. Now, let's say x, let's take a parameter x is greater than or equal to say, no, not x, 10 is greater than 5, 10 is greater than 8, right? So if you want to make this an inequality, then what should you do? You can add 2 here. If you add a 2, then 10 is equals 10. Do you agree, Alan? Perfect. So then in that case, we can say that by adding a positive constant to the lower side, we can make an inequality to an equality. Agreed? So that is what we did here in the second step. So we had a parameter which is greater than or equal to another parameter in the right hand side. So we added a positive constant and we named it Sgen, and depending on the inequality sign that we have, if we have ds greater than delta q over t, then we have to have a positive value to match the two sides. And if ds equals delta q over t, then Sgen is going to be 0. The constant is going to be 0. Did I clarify it for you, Alan? Perfect. So the idea I wanted to establish is Sgen is always greater than or equal to 0, and entropy generation, the property that we are learning here, can never be negative. Entropy generation is not going to be negative, right? Entropy generation is not going to be negative. It's always 0 or higher. For reversible processes, in this expression that we indicate with the arrows, for reversible processes, ds equal to dq over t along the process line. And there, the entropy generation becomes 0. For reversible processes, entropy generation is 0. And for irreversibilities, for irreversible processes, entropy generation is always higher than 0. Any case, no matter what, entropy generation cannot be negative. If you don't understand the derivation, it's fine. I just wanted to provide you with food for thought. Like, I just didn't want to just give it to you and say, okay, I tell you entropy generation is greater than or equal to 0. So I just wanted to show you that there's a way that you can see things, right? So by any means, if you feel this is too difficult or you did not understand the derivation process, or you got somewhat of the derivation process but not very clear, but still it's fine. In this course, I'm not going to test you for this derivation or this level of depth. But what I wanted to do is to explain you this is how we come across that entropy generation is greater than or equal to 0. And in summary, as seen here in the bottom of the slide, for reversible processes, entropy generation is 0. For irreversible processes, entropy generation is greater than 0. So any doubts, anything not clear about this slide? Perfect. How about the others? Are we all getting it right? Because I want to hear confirmation from all of you. Okay. Perfect. 1 second. And now let's go to the process. Similar to our first law equation, after much deliberation about the theoretical aspect of entropy and all these other parameters, now we are finally into somewhat we can relate to the calculations. As engineers, we are very good at calculations than theoretical discussions. Sometimes some of them are really good at theoretical discussions, some of them are really good at quantification, some of them are good at both, right? So similar to the previous case, now we are going to discuss the entropy balance equation for a closed system. Okay, for a closed system, entropy change occurring during a process involved in a closed system, then we can say the entropy change is equal to total entropy input minus entropy output plus entropy generation. I'm sorry, give me 1 second. Okay. And we'll learn during the last slide that entropy generation is going to be this one, right? In a closed system, we agreed that there's no mass inflow or mass outflow. Therefore, when it comes to entropy, only heat component is there to take in and out the entropy, right? So for a closed system, a process happening to a closed system, entropy change in a closed system that during that given process can be written as S2 minus S1. And entropy transferred in and out of the system, heat transfer, can be written as this one. And then here's our good old friend entropy generation due to irreversibilities, right? Are we clear about this equation? Perfect. So let's go in deeper and discuss when it comes to that point. We'll discuss how to find S2 minus S1 and how to find the delta Q over T, how to find entropy generation as we move along. And we'll don't worry as of now. Today is very heavy on theory, but we'll use this theoretical knowledge to and to do our calculations, and then you'll get a better sense, right? But at the same time, if you do not understand anything, please feel free to stop me and ask questions. Now, we can define the second law in terms of entropy generation. You remember in the previous lecture, we used Clausius equation, Clausius statement and Kelvin-Planck statement to interpret the second law, right? So these two names are familiar to you already. And then it's interesting to see that entropy generation can be used to see whether our devices align with these statements. So please read through the first bullet point. It says any device that violates the Kelvin-Planck or Clausius statements have a negative entropy generation. So either ways, it means if our entropy generation during a process is greater than 0, then we say that it is an irreversible process. If our entropy generation during a process is equal to 0, then it is a reversible process. If our entropy generation is less than 0, then it becomes an impossible process, or it violates Kelvin-Planck and Planck or Clausius statement if it was involved in a heat pump or a refrigerator. So let's say during a given process, I get negative 10 as entropy generation. What can you say about this process? Is it impossible or reversible or irreversible? It is impossible because we cannot have a negative entropy generation, right? So if I said my process had positive 8 entropy generation, then what can you say? Then what can you say? It is an irreversible process. Is it possible or not? Can it happen? Can it exist, or can this process take place in real world? Is it possible? It can happen, right? So in a given process, if I have zero entropy generation, what can you say about this process? Is it reversible, irreversible, or impossible? If my entropy generation is zero, what can you say about that process? It is a reversible process. And can this happen? A reversible process, can this happen? It is harder to achieve, but it's not impossible. With our practical limitations, it is almost impossible, but it does not violate any theoretical limits. You are right, Desa. Under practical conditions, it's almost not possible to achieve. But is it impossible? It's not impossible. Are we getting it clear? Perfect. And we can use this criteria to determine whether a process is possible or not. So somebody comes to us and say that, okay, I have a mechanism to create negative entropy generation. So we say that according to current knowledge of thermodynamics, we cannot have negative entropy generation. So your process or your calculations are wrong. Either one has to be wrong, right? There's something wrong with your calculations. The process cannot be wrong. I mean, there could be any process and somebody interprets the process in a wrong manner and they get entropy generation to be negative. Such a process cannot take place in reality. So the last point, a real process happens only in the direction of decreasing the quality of energy. So you remember from the last lectures, we discussed about the quality. It only happens in a way that the quality of energy is decreasing because our coffee cup had thermal energy and it flowed to the surroundings in a winter day. So the quality of energy dropped because the temperature dropped in the coffee and the temperature that of the surrounding does not have the capacity to return the energy back to the coffee as well. So the ability to do work reduced, the quality reduced. Or else we can mean the same thing. A real process happens only in the direction of increasing the magnitude of disorder. So entropy generation is an indicator of the magnitude of disorder occurred during a given process. So this brings up an interesting notion. Let's say if we had a positive 10, if we had a positive 10 as our entropy generation during process A, and if we have positive 5 entropy generation during our process B, so which created more disorder, process A or process B? Process A or process B? Process A created more disorder because it created a higher entropy generation. And so from a thermodynamic efficiency point of view, what is closer to a reversible process, process A or process B? Process B is closer to a reversible process, right? Excellent. So would you prefer to have process A or process B in your machine? What would be better to have in your machine or thermodynamic process? It is better to have process B. Excellent. Because we always want to get closer to the reversible conditions. That is when we achieve the highest possible efficiencies, right? So we don't want to go lower on that. So this gives an interesting understanding. So lesser the entropy generation, the better efficiency that we can reach to, or further we can get closer to reversible process conditions. So do we make sense? Are we all in agreement and clearly understand what we discussed here in this slide? Perfect. Let's move on. Okay. Now, this is a common confusion that students and many professionals tend to do, like not in professional environment, you're not supposed to do that, but delta S or entropy change of a system and entropy generation, are these two the same? That's my first question. Entropy change of a system and entropy generation, are these two the same? Yes or no? Entropy change of the system and entropy generation are not the same, because if you go back here, this blue portion is the entropy change of the system, and this orange portion is the entropy generation. So these are two different entities. So these are not the same at all, right? And let's investigate the similarities or differences of these two properties. Entropy change is a state property. Delta S only depend on the initial and final state. The path does not matter. The path does not matter. So specific entropy can be found from property tables or calculated using CP and CV values. We'll discuss how to do this in the coming slides, so bear with me. So these are state properties. Similar to internal energy enthalpy, these are state properties. Therefore, we look into our pressure and temperature conditions and we go to property tables, or we use ideal gas assumptions. We can find this, right? So entropy generation is somewhat different. It's a measure of magnitude of irreversibilities in all real processes, right? Does entropy generation, now comes my next question, does entropy generation change based on the process? Does entropy generation change based on the process? Exactly, excellent. It can change based on the process we follow, right? Because it's not a state property or anything. It's a measure of irreversibilities. So as we compared the two processes in the previous example, plus 10 entropy generation and plus 5 entropy generation, that can happen. That can happen between the same two states. It's fine. It can happen. Depending on the process, the entropy generation change. But entropy change does not change depending on the path, because entropy change depends only on the states, initial and final states. Are we crystal clear on this one about the differences of these two, entropy change and entropy generation? Are we clear? Anyone? Perfect. Awesome. Now we discuss how we can use the entropy generation to interpret the second law, whether a process is aligning with the second law or not, right? So I'm not going to re-explain that part, but we used entropy generation to see whether a process is irreversible, reversible or impossible. Now, in general, entropy generation, the number, the quantitative value is not equal to entropy change. Delta S may be positive or negative, but entropy generation should always be positive or equal to 0, right? So can delta S have negative values? Yes, it can have negative values. Can delta S can have positive values? Yes, it can have positive values. Can delta S be 0? It can have 0. It's all good. But entropy generation, can it be negative? Entropy generation, can it be negative? No, not at all. Not under any condition. So if you see a negative entropy generation, that's a big no. That process cannot happen. That is an impossible process. Then you identify that right off the bat. And entropy generation, can it become equal to 0? Can it be equal to 0? Yes, it can be equal to 0 if the process is reversible, which is the theoretical best conditions that we can achieve. But for real world processes, it is always, entropy generation is always greater than 0, right? So that is the differences between entropy generation and entropy change. So similar to enthalpy, internal energy, entropy cannot also be measured directly. So we calculate it with respect to a chosen point. You remember my example. For us to calculate a distance, we need a starting point, right? So we can take an intersection of the highway and say, okay, from this point, when you go this far, it is 1 kilometer, right? Similarly, for internal energy, enthalpy, and entropy, we define a reference state, right? For different tables may have different reference states, it's fine, but in our calculation, in a given calculation, we should use the same reference point. So in your property tables, the properties that you see are defined compared to a given reference state. At saturated liquid at 0.01 Celsius has UF, HF, and SF equals 0. So this is the reference state. It's like Harvey and Richter Street intersection. We consider that to be our starting point. That is our reference point. That is 0 for everything. Then we say, okay, if you go this way, that is this much and all these lengths. Similarly, for these properties also, we define a reference state, and when we are deviating from the reference state, we define this is your property states. For different substances, you may have different reference points as well. You see it here, right? Now, in our evaluations, in thermodynamic evaluations, we are not interested in the absolute values. What is this and what is that point? But rather, we want to see the change of a property, how much internal energy of this system changed, how much of a change we observed in enthalpy of the substance, right? So that is why we are more interested in the enthalpy or entropy or internal energy changes than the absolute values. So in that case, the reference value, as far as we keep it the same throughout the entire calculation, if we pick a different reference value, it's not going to add a difference. Let's say we pick we decided to calculate the distances throughout the kilometer with reference to intersection of Harvey and Richter. That is one intersection A, and we get certain houses, house 1, house 2, the distance between house 1 and 2. And then somebody else decided to calculate all the distances with reference to junction B. And they want to calculate the distance between 1 and 2. Would the reference junction change the distance between 1 and 2? Anybody? Would that make a difference to the distance between state or house 1 and 2? It doesn't make a difference, right? So let's say this is a road and our reference point A is here, our reference junction B is here, and house 1 is here, house 2 is here. The distance between house 1 and 2 is not going to change depending on the junction we picked. From junction A, we might have 10 kilometers to house 1 and 20 kilometers to house 2. The difference will be 10 kilometers, the distance between the two houses. But this 10 kilometers is not going to change depending on the junction we pick. Similarly, depending on the reference state we picked, the properties are not going to change. The differences of the properties are not going to change. But we cannot mix up junction A and B in our calculations. We cannot measure the distance to house 1 from junction A and distance to house 2 from junction B and then subtract to get the difference between or the distance between house 1 and 2. In summary, as far as we keep all our reference points at the same number throughout the calculations, we are fine. So that's why we ask you to stick to our property tables and use that throughout our calculations, throughout our course. So in your practical life, when you go out to the industry, if you want to calculate the entropy or enthalpy or whatsoever, so you can use online calculator or whatsoever, but use the same calculator throughout your calculation. That's very important, right? Okay. Now, the good old property tables. So now, by now we know how to find specific volume, and we know how to find internal energy, and we know how to find enthalpy. And similarly, for compressed liquid, if we know the pressure and temperature, then we go along this line and we can find entropy as well. So finding entropy is nothing different than finding any other property from property tables. So again, for superheated vapor, it's the same thing. You look for entropy, and then you can find the specific entropy value, let's say 100 at 100 Celsius and 10 kilopascals. You look for the pressure and temperature, and then you locate the point, right? Saturated tables, again, the same thing. There was an important observation that we agreed before with the parameters or properties that we learned earlier. For compressed liquid region, that's a TS diagram. For compressed liquid region, if we have the dome here, for the properties here, we can find the property on the line at that given temperature, saturated liquid line for that given temperature, and take that value as the property inside this compressed liquid region, right? You remember, if we have pressure and temperature of a given substance in the compressed liquid region, we just took the temperature and found VF value for that temperature and used that as our specific volume for that substance in the compressed liquid region. Similarly, we did the same for internal energy and enthalpy. And what we are saying here is you can do the same for entropies when you are trying to find that value in the compressed liquid region. the differences would be minute. So you don't have to worry about that. Are we clear here about this assumption? Are we clear? Perfect. Now, you remember we developed the relationships between VF, VFG, and VG with respect to the quality of the substance in the two-phase region, right? We can use the quality with VF and VFG or VF and VG to find the specific volume at that given state, right? We learned this in the very beginning of the course. Similarly, when we introduced ourselves into enthalpy and internal energy, we learned that the same relationships are there for UF, UFG values and HF, HFG values, right? Now, what we are saying here is the same relationships, similar relationships, not the same thing, similar relationships for entropy with the quality of a substance inside the two-phase region, it exists as well. Are we clear? So in a given substance, if we wanted to find the quality, if we know the entropy values at that given state, and then we can write S into S minus SF into divided by SFG. We can do this, or we can do the other way around. If you know the quality, you can calculate the entropy using the quality and the values you find from the property table. Do I make sense? Perfect. And this is a TS diagram, and similar to other diagrams, inside the two-phase region, pressure and temperature are not going to change. Constant inside the dome, we have constant pressure and constant temperature values. If but if the volume is constant, then the shape of the lines will change inside the dome, right? So we'll not be dealing too much with the TS diagrams, but this is just for you to understand the idea. And similar to other phase diagrams, two-phase region inside the dome and compressed liquid region to the left, superheated region to the right, and critical state at the top of the dome, and saturated liquid line as seen here in the blue color, and saturated vapor line as seen here in the orange color. So this is just to give you an idea about how would a TS diagram look, right? So we'll see like how we deal with TS diagrams in the coming questions and coming lectures. We will have a bit of use for this diagram as well. We'll see how we are going to use it, right? So entropy change of a solid or liquid mainly depend on the temperature. So for a solid or liquid, to calculate the entropy change, you can use this relationship. Here, C is the specific heat. You know that for solids and liquids, for solids and liquids, Cp equals Cv equals C, the same value. There's no different values for constant pressure specific heat and constant volume specific heat for solids and liquids. Those values differ from each other when it comes to gases or vapors, right? And if you know the specific heat values from the property tables, if you know the temperature values during a given process of a solid or a liquid, then you substitute the numbers in this equation and you can find it, right? The important thing about this one is you always substitute the temperature values in Kelvin. So ideal gas, no. For ideal gas, Cp Cv equals C does not exist for ideal gas. So for gases, Cp and Cv are different values, right? So you know that from previous lectures. That is what we've been dealing with. When we are dealing with the gases, it has two different numbers. But for solids and liquids, it's the same number. Okay. And this is the natural log, right? And I forgot to tell you that. Natural log, this is the natural log of T2 divided by T1. So learn how to use natural log in your calculator before the exams, right? If you have already learned how to do it, that's fine. Otherwise, learn how to use the natural log in your calculators, okay? And to find the entropy change of an ideal gas, we have this relationship. This is one way of doing it. We can get the values for ST2 and ST1 from the property tables. A7.1, A8 for the given two temperatures, right? And then gas constant, we already know how to find it, and the pressure values here, right? So you can use this equation whenever you have information. You can use this equation, but we will not be using this equation as commonly as the other equation. We will not use method 1 as commonly as the method 2 that we are going to learn right now. So in exam, please use these two equations, right? Don't use method 1. I just added method 1 for your reference. For ideal gases only, right? So for ideal gases, you get Cp naught and Cv naught, and you can use either of these two equations to calculate the entropy change of an ideal gas during a given process. Importantly, always substitute temperature in Kelvin. And for a closed system, can we substitute absolute volume or specific volume? Does it really matter here in this equation? V2 and V1, can it be specific volume? Can it be total volume? Or it doesn't really matter? Either of these, either of the two are fine. Both are fine or not. Let's assume that for a given closed system, there's a mass, fixed mass, and at the initial state, the volume was V1, total volume. At the final state, the volume was V2, right? So V2 divided by V1 equals V2 divided by M, V1 divided by M. It doesn't change a thing. So this essentially the ratio between the total volume is equal to the ratio between specific volumes. So, right? So we can use both. It doesn't really matter. Are we clear? Yes, always use method 2 unless specifically asked for method 1. So stick to method 2, I'd say. For ideal gases only, right? So it's very important even in the exams, like you have used, not, I mean, not Deja personally, but I mean, as a class, you have used ideal gas assumptions for refrigerants. Don't do that. You cannot assume ideal gas behavior from the refrigerants. First of all, refrigerants cannot be ensured to be in the vapor region. We don't know whether it's a vapor or a liquid because it just says a refrigerant, right? Refrigerant R134A, like we don't know whether it could be a liquid or it could be a gas. Either ways, for refrigerants, it's very non-ideal behavior. It has very non-ideal behavior. So don't use it. For water or water vapor, don't use it, right? So either ways, Don't use it for water. Ideal gas assumptions. If you see hydrogen, nitrogen, and CO2 in certain conditions, so like when you see gases like that, then think maybe I can use it, right? So other than that, inert gases with very low bonding capacity, then you can use it. But other than that, don't use it. Whenever you have property tables, always go to the property tables. Please check whether you have property tables. That would be one big check that you can have to avoid this mistake, right? So to give you a chance, I only deducted some marks for using ideal gas assumptions. If your calculation was right, assuming ideal gas behavior, then I gave marks. But that is wrong. You should get 0 marks if you assume ideal gas behavior. Just to give you marks, I marked it. I asked the TAs to give you that mark. But in the finals, you won't be getting that mark. Okay? So don't do the same mistake again and again. Please learn from that mistake and build on that. Okay. Are we clear? Any questions so far? Perfect. So that is it for today. And I know that is heavy on theory. Today's lecture was heavy on theory. Even it was difficult for me to explain, and I am pretty sure it was difficult for you to listen to and understand at the same time. But please go through the content again, and if needed, please review the lecture recording and familiarize yourselves with these concepts. And tomorrow we'll be looking into the calculation procedures and how we can use the concepts that we learned today to do calculations and to assess closed system processes. Okay, so that is it for today. If you don't have any questions, please feel free to leave.